Relevance of the building. Some of you know me, I think. I mostly work on millimeter wave and also optical, now quantum computing, so a broad range of topics. I think some of that will be covered by you guys today. So this session is the first one, the 9:30 Cryptography. We have 4 speakers sharing their research results, and we'll have to figure this one out.
Yep.
So if you have uploaded your slides, I think it should show up pretty easily.
No, I think
Or do we need to connect? Everyone needs to connect with her?
Yeah. So you have your Teams information have been shared with you, and you would be connecting to the Teams session, and then you'll be sharing your content through that.
Oh, I see.
Yep.
And then where's the is there Wi-Fi?
Yeah. So Wi-Fi information should have already been shared with the visitor Wi-Fi information. Should have already.
But is it possible to share it once more?
It's easier if we just have one laptop.
That's perfectly okay.
Yeah, let's just have,
Yeah, if you this one, they said one downstairs. Let me just double check if you guys if we have another
What
one.
they told us was give me a laptop with all the uploaded presentation. Right.
Okay.
Go from there.
Yep. So I will double check. Just give me a moment. I'll verify this.
Does anyone have the Wi-Fi?
No, I
Yeah,
don't.
you should have gotten an email
Sent an
from
email.
No Reply Americas. No Reply dash Americas.
Oh, you probably thought it was spam.
Yes.
Sounds like
So look for No Reply dash Americas dash IBM Internet. And you would have gotten a personalized username and password. And I believe that's for 5 devices, right? Up to 5 devices
okay.
per person. So, and then I think you select,
It's probably a good test to see whether you can just get away with tethering your phone to
That I am. That's what
That's what I'm doing right now.
That's what I'm doing right now too.
you can as well. You ask for Wi-Fi. So.
Hopefully it doesn't work well, so we can motivate the next version. Right?
But that's what we want, right? Ubiquitous coverage everywhere we go.
Wi-Fi can't work so well. Wi-Fi works so well. Not much to do.
No, there's always much to do.
So,
your phone's twice as fast as the internet Wi-Fi.
You just tested it?
Yeah. I got
Is it
200
no
megabits per
high
second
level
versus
line?
100.
What's that? Yeah, no, I sure you. I found it. That was very. This is the email that I got. No replies dash America dash IBM. I do if you just search IBM.com, or at least for me, I don't have many emails from IBM.com.
Okay, so she's in one.
yeah.
So Jerry just told me that downstairs there was one, and then upstairs there was somebody was supposed to bring in a laptop.
Yeah, I need to right back.
Oh, he said that you were gonna bring. It's okay.
All right, sorry about that.
It's all right. I'll just use mine.
Okay.
Just give me a few minutes, and I will get all of your content in here. So.
Excellent. Thank you so much.
And the network is IBM or ThinkLab?
Oh, that's a good question. Let me see. I think IBM Internet is what I'm trying to say.
It's IBM Internet. And then it'll,
Wi-Fi and
Yeah, that seems to work.
and then it'll ask you for username and password.
Okay. I didn't really think I thought that was spam.
Sorry about that. We'll have your slides up in just a moment here.
we have 4 speakers this week for sure. We have Zhong from Yale University, or anyone else from Yale University who can present that one. Let's see, I don't know if you can find them.
Gotcha.
It's registered.
Right. All right. How about our second person?
Ali is there,
Ali?
and Krishna is here. Reza,
I'm going to present. I'm not Reza, but I'm going to present. I'm the co-PI. He's late. Yeah. I'm Kamal.
Well, very good. Just like the auditorium, we have 3 of the 4. So, yeah. All right. So you'll be going first then.
Yep. Cool.
Where did you get the Microsoft? So
Yeah, that's
give the team for this?
No, I don't, but I'm not able to get into the internet.
Of course.
Getting feedback.
I did get the email, but it doesn't seem to work. I have the email, I have the
Tried
password.
again, it didn't work to me the first time, then it went out and then.
I have to send them.
Yeah, no, I have the password.
You haven't sent it yet?
I haven't.
Username.
Can I use my laptop?
Looks like it's just wireless. So if you connect to the Teams meeting,
Where is the Teams meeting invite? Was that also in an email?
It was shared.
I don't
An
think
email?
we got that information.
Oh, we don't have the Teams. I don't think
I
so.
don't think so. I think it might have only been shared with the people who are attending remotely.
Oh, okay, so then we can't even
Do
do
you
it anyway.
have the slides for the presentation?
I mean, it's in that
didn't
folder.
update.
Oh, it's an apple, okay.
You guys can go
I
first.
can't.
Yeah, maybe.
I think Ali's.
Maybe we can start with the second person.
No, that's what he's gonna do, but they're also having
they
same.
all have the same issue.
Oh.
So there's a,
No,
So the agenda page had like, I guess if you want to hack it right now, the agenda link URL had like a way to register. I mean, worst case, we can register right now to be a remote attendee and maybe get a Teams invite.
Teams invite.
Yes, sir, I have the Teams. I am connected, as you can see. I just don't have the slides, so I'm
But
just
you
looking.
had done that one share that.
There's a SharePoint where everybody's uploaded. He's just gonna give it to me. I don't have access to it.
Send the link to all the, if we can just get the email, send it out right now, the Teams link.
The Teams link?
You have the Teams link, then you can send that.
I just have a picture.
think the slides are
of
already
the
connected.
credentials. I'm not sure, but it should be.
So
Maybe one of the
on the
meeting
Teams
items.
meeting, can you?
Yeah, so
invite
How
out
to access it.
Um,
restrictions from their own.
Oh.
I don't
yeah.
know what the problem is.
Right there. Do you have, what is your email address? I can send the invite to?
len.zhong@yale.edu. Oh, I could airdrop to you,
Oh, yeah, that would be
but
perfect.
are you CR4?
No, but give me a moment. I will turn my Bluetooth on. So just give me 1 minute.
MacBook Pro 3?
Yeah.
That's you?
I would be Michelle, so, sorry. Yeah, did that one, yes.
That's you.
Yeah, that's, you wanna just drop me the slides until
This seems
he can get me all the other slides.
connectivity issue, no.
Sorry about this, Yeah. I have
Means
that.
that nobody can
So.
It's actually the way to
5
start a wireless.
seconds.
discussion, right?
But it's a secure system, nobody can present.
5 seconds?
Because the,
Do you want to try again?
Yeah, it got disconnected, so.
the people who are actually remotely present,
Dropped off, so.
and
Got
nobody else can access it.
Which one is this?
MacBook 3. Yep, that one.
so you don't need that. That's what I didn't even realize that I had a Wi-Fi here.
Yeah.
Because I think it said no replies, it sounded like total spam. But the subject line, you think is complete spam, so.
I just hope I have a wire.
If you wanna,
So are we doing the old fashioned way of just connecting directly?
I'm in the last one.
Ignore.
Are you in this one?
no, I'm not getting.
Oh, you're not in today, not in the morning one, or you're not in the first.
Looks like you're getting mine.
I'm getting yours, but it.
It's always that something remaining here.
Yeah.
I can start.
Yeah, if you, in the meantime, if you, are there any remote participants? If not, we can just start. If, oh, there is one.
I just shared it, so you should have it.
it's not coming through. That's the problem. It stops right at the end. So if you want to start sharing, I'll figure out a way to do this.
Happy word. Should I use the word option?
Yeah, we have. Oh.
Still stuck on the last. You should always have like the last 5%.
It makes me realize that, oh, we've got that plugs here. Yeah. I was about to just say that, oh, this makes me realize that this is really make a lot of money to make your auditorium is really nice, but then technology comes along.
This is your slide showing up, and I'll figure out one as soon as I get the slides for the remote parts. I'll share that with them.
Or you can just do the Teams invite.
Yep.
You can invite all the speakers.
Yep, I
Okay,
can.
I'm gonna start.
If you wanna hack your
Hopefully that's back on track. Hi, everyone. I'm Ali Niknejad from Berkeley. I'll be talking about our project. Just jump in here. The title of our project is Wideband, Next Generation Terabit per Second Millimeter Wave Communications and Networking. OPI is for our Niknejad. The objective of this project is to investigate extremely wideband communication, 20% fraction bandwidth, up at frequencies above 100 gigahertz. So we're talking about 20 gigahertz of bandwidth. How do you turn that into terabit per second efficiently and deal with channel impairments that you're all aware of? We also want to understand technology limits, in particular CMOS technology, and also packaging and building arrays and getting the signal from the chip to the antenna, which is actually non-trivial. And we also have a sub-project involving mostly undergraduates, which is building a multi-user MIMO system with our previous generation 140 gigahertz transceivers that we built in other projects, such as the Jump 1.0, and we continue to work on it under Jump 2.0. So the challenge is, of course, when you have such a wide bandwidth, that channel dispersion, other frequency-dependent non-idealities of the channel come into play. The package transition is very critical. We spent quite a bit of time on that, getting from the chip to the board. And then performance of CMOS above 100 gigahertz is very limited. Another issue that comes up is when you're building a very large array, which is required when you're going to higher frequencies to get the required EIRP for long distance communication, your array size is delay across the array is actually a substantial fraction of your bit period. In fact, it will be longer than your bit period. So you have issues with intersymbol interference, and another common problem is beam squint, which I'll talk about later. And so these things can limit bandwidth. So our key accomplishments so far, we've done a very nice systematic study of the packaging limitations. We've actually fabricated some packages and done some measurements. I'll present that. We've proposed the spatial FFT to solve the beam squint issue. Published some papers on that. And we're also working on a measurements of a high EIRP transmitter at 140 gigahertz. Again, this was built previously, but we're characterizing it in the lab to understand how fast we can go with our technology. So the future work is undergrad students are going to build up a full link at 140 gigahertz. We're continuing to look at the active devices and seeing are there techniques that can reliably give you gain at higher frequencies, but also the bandwidth that we need. And in the proposal, one of the things that we thought would be really neat to look at is some efficient way of generating multi-tones, multi-carriers, similar to OFDM, so that every sub-channel is relatively narrowband, and so you could actually modulate independently. Of course, that's going to work. The problem is if you build 10 transceivers at 10 different carrier frequencies, power consumption goes up by a factor of 10. So how do we keep the power consumption reasonable, but still use multi-carriers? And this is kind of an analog multi-carrier because we're talking about 20 gigahertz of bandwidth. We can't just
digitize it and then do that in the digital domain. Okay, so the chip to package transition, I've already motivated to you. If we look at just building a standard transition, we're looking at 2 to 4 dB of loss. And this loss actually happens at the most critical points, right? It happens on the receiver, so it adds to your noise figure. It happens on the transmitter, reduces your transmit power. And so if you do a back of the envelope kind of calculation, this is the aggregate capacity you can get out of the channel. As a function of this loss, you can see that you're going to drop from terabits per second down to 250 megabits per second, just with a few dB of loss. So what we really need to make this work is sub-dB loss transitions. So why are there problems? Well, at these higher frequencies, the dimensions that we typically use in integrated circuits become a fraction of the wavelength. So your structures can support multiple modes, and in particular, waveguide modes, which have TE and TM components, which have low frequency cutoffs. That's why we don't see them when we're working below 100 gigahertz. When we go above 100 gigahertz, we actually get into the above the cutoff frequency and we excite those modes. So that's the problem. So if we model these to make sure that we understand kind of the mechanisms behind these modes, and we've done extensive EM simulation. Here I'm just showing you different kinds of transitions you can have from the chip to the board. You're going to go through board or package, so more or less the same thing. But the problem is you're going from chip scale dimensions, which are tens of microns, to kind of ball pitches and landing pad pitches of hundreds of microns. And so if you're using a low-cost packaging, it can be anywhere from 100 micron balls and 100 micron pitches to like 60 micron balls for the smaller pitches, but actually all the way up to 250 microns for the lowest cost manufactured kind of ball pitches you have. So you can try different structures. Here, these simulations are showing you the pointing vector, and you can see there's, in all of these structures, there's good mode confinement, that energy is not leaking out. But some of them are just impractical in terms of how much die area they take. Like for instance, this structure has really nice confinement, but it's just too much area for each transition. One of the ways that we actually keep this strip line, if you look at the strip line modes, which is TEM versus the TE modes in this particular example, you can see that the propagation characteristics are very flat. Z0 is very flat for a TEM mode. That's the one that we like to use. This TE mode, the cutoff frequency comes up, and it basically has a non-linear, also non-uniform Z0. That manifests itself in, like, if you look at the maximum gain you can get through this transition, you actually get notches when these modes pop up. So we've looked at different structures that prevent these notches, and this is a simulation result. Just jumping kind of through the summary. If you're interested, we have a paper in archive that's already been published. But these are two structures that we ended up using. One is at 140 gigahertz with an organic substrate. The other one is at 200 gigahertz with an organic substrate. Taped out in two different processes, a 20 nanometer bulk CMOS and a 16 nanometer FinFET process. And the results that we have are actually, spectacular. We have a dB of loss. These are simulation. Very wideband performance, actually all the way up to 300 gigahertz for this 16 nanometer FinFET process.
Sorry, Ali, just because I don't know this area. This would be going to the antenna from the chip, or that's the RF signal, that strip line? Is that how I interpret that?
Transition from the chip into the package.
And then that strip line would go and then to the antenna.
Yeah.
And you're to get, okay, sorry, just to.
So once you get onto the board, of course, there's going to be loss.
Yeah.
But the nice thing is everything is more uniform, right? But here you have a lot of non-uniformity, and you're transitioning from different transmission line modes on the chip to exciting the structure that can support many, many different modes. In fact, radiation if you're not careful. So these are our measurement results. The package that we used was an ABF GL102 organic substrate, high volume package. 75 micron pitch bumps, and with roughly 150 micron pitch between the bumps. So the balls are about 75 microns. So you may recognize these are not copper pillars, which are more expensive and less available. This is standard packaging. So we built this, we built the chip, we built the package. Essentially, in this experiment, we're just, what we have is transition from one chip to another through the package so we can measure the total loss, which includes the actual transmission line in the package. And then we can de-embed that by having standard TRL de-embedding structures to just isolate what the transition looks like, which is what we're after. And after doing all that, we've been able to do measurements. We have about half a dB per dB a millimeter of loss in the package. We've de-embedded the feed lines from the measurements, and putting it all together, we've actually demonstrated, these are the measured results. We've demonstrated that they match pretty closely with simulation. You can see we're predicting all the modes and all the resonances that happen in the channel, this wideband channel, 124 gigahertz. You can see that our measured loss is slightly higher, and there's surface roughness and things that we couldn't model. All right, I have about 5 minutes left, so I need to speed up a little bit. Okay, as I mentioned earlier, that we have a test bed in our lab at 140 gigahertz, and I have a group of students led by a graduate student, Jose. Lots of undergrad students, amazing undergrad students are working with us. They started out with Haley, who came from Cooper Union as an NSF REU Superb student. And then these are all Berkeley students, Sanjay, Tyler, Shekhar, Nikhil, and Alejandro, have taken courses and gotten interested in the subject. And so they're all at various points working on this project. Right now, 2 of them are actively working on it. And the other good news is that through this project, actually Haley got really interested and applied to Berkeley, got accepted, so she'll be joining us in the fall. So what the students are doing is they're taking a chip module that we developed under, initially, mostly under the Jump 1.0 program, but also continuing in Jump 2.0. Call this the Charm IC. It has 4 transceivers on it at 140 gigahertz. We've packaged these onto a substrate where we have 16 RX and TX elements. And then we put this onto a board, and the students have helped to create all the software to bring up all these channels and program it independently. You can see roughly some of the specs over here. This supports a 14 gigahertz bandwidth, consumes about 100 milliwatts RX TX on average. And what we've done here is some measurements in the lab. These are measurements with pretty much most of what I'm showing you here is with test equipment. I'll just highlight some of the cool results. Probably one of the most interesting results is that we were able to get up to 140 gigabits per second per channel using just the transmitter. And so, if you take that number and put a few MIMO channels together in a multi-user configuration, you can actually see the pathway to getting up to terabits per second. With our own RX and TX talking together, we've been able to get up to 24 gigabits per second, and we're limited by all the impairments of phase noise and nonlinearity and things like that. So this is active work. This is what it looks like in the lab. This is the base station, and this is the transmitter. And this is all being run now by undergrads, so it's really exciting. Let's see. Also just another highlight is Rodi and Schwartz actually featured our Charm IC at IMS this year. It's a big show in Washington. This is Hisham and Ethan, the students who developed this module. And using this Rodi and Schwartz kind of equipment, it characterizes your system over the air. We were able to measure link performance, EVM, not to the high data rates that we'd like, but we've been able to get things like antenna patterns. So it's been really cool collaboration. We got some press, so that was nice. Okay, I'm going to unfortunately breeze through the rest of my talk because of time limitations. If you're interested, come to the poster session. In our last review, I talked about this spatial FFT for beam split communication. And very simply put, most RF systems that use RF beamforming are basically using a phase shift in place of a time delay, right? What really happens is you have a wavefront coming in containing many frequencies. And if it's a narrowband system, you can represent the time delay from one point to another with a phase shift, right? The problem is if you have a broadband system, then that's not accurate. And so you're actually not summing things coherently. And this is why you get the beam squint. And this doesn't happen when you're looking broadside. Broadside, everything comes in at the same time. It happens when you're looking at signals coming in at different directions, where now the time delay becomes more important. So the more you steer your beam, the worse the situation gets. And doing some calculations on coherence bandwidth or on intersymbol interference through the beam squint, you can put a bandwidth limit on how many, depending on the angle of arrival and the antenna size, what your bandwidth is going to be. This is the normalized bandwidth. So one way to get around this is very simple. This whole spatial, you can think about this as, nature doing an FFT for you, right? Because you're summing signals from multiple antennas, each with a different e to the j theta, right? That's a spatial FFT. And if your array is uniform, then it's e to the j theta plus e to the j2 theta, and so on. So it's doing it discrete. It's actually doing a shut up. So it's doing a discrete DFT for you. If you could do an inverse DFT, you could undo all that, and you'd have basically perfect summation, coherent summation at all the different frequencies. The problem is, of course, the matrix size. If you do this, depending on this, if you have n antennas and you do this for n's 1,000, then this is 1,000 point FFT with 2 gigahertz or 20 gigahertz of bandwidth, or 100, whatever the number is. It's too expensive. So what we've investigated is doing this with a reduced number of carriers. So we do sub-carrier, and we've demonstrated with OFDM that you can make this work almost as good as doing a full FFT across the whole array, which makes sense. If you group a few carriers together, right, a few antenna elements together, their phase shift is going to be more or less the same. And so this is why the technique works. We've published a paper on this. It's another archive paper. So if you're interested, I can point you to that paper, and it's in the slides as well. This is just a quick slide I wanted to flash because when we did our last review, we were asked to investigate how this impacts PAPR. And so the good news is it doesn't. It's actually pretty good. I have some more slides. I'll stop here, and please come talk to me if you have any further questions. Thank you.
The next speaker is Zhong from Yale University.
So we're gonna have time for questions.
I think we are very short on time, folks. So maybe during the break,
Do you want to just give me the name of this slide?
Oh, it's 2024.
This is all of them now, so.
Is it changing the file name? Doesn't seem to be there. Oh, this one.
This one?
Yeah. Maybe the second one.
Okay. There you go. And I'll share 1 second.
Good morning, everybody. And I think we're going to switch gear from Ali's wonderful talk to the subject of software. I think circuit researcher Ali will solve all the hardware problems. The remaining is basically software. That's where I come from. So I'll give a little background of the project, and I talk, give updates about what we have achieved in the past year and two. So I'm actually, every time I talk about my work, I confess I don't understand wireless at all. I'm not a computer engineer. I build things, and then people ask me, why do you work on wireless? Right. So I looked at wireless. I think wireless is a very good problem for computer scientists. It's based on two fundamental facts. Number one is spectrum is scarce, although by the research of Ali and other people, we get to higher frequency, we have more spectrum. But if you look to like what do we have sub 60 hertz? It's fixed, right? And then on the other side, computing is cheap and getting cheaper and cheaper. So basically, in wireless, what we're doing is basically throw in more and more computing over the years and to make spectrum use more efficient, right? Massive MIMO basically is one of such tricks. The people who really understand wireless actually figure out how to use computing to trade out for buy more efficiency. So what we did before the RINS project is over a decade. My former student, Police Shipper and I, it's basically we built like multiple generation of massive MIMO prototype starting from 2011. That's the world's first massive MIMO prototype. Thanks to National Science Foundation's support of that. After that, we refined that and also eventually led to develop a network of them that we deployed on the rooftop of Rice University, allow us to do networking research with massive MIMO base stations. And of course, Clay Shipper went off to co-founded company, and now if you're interested in buying some of the test bed, you actually can get them commercially, and also the unless funded Power Renew project actually have some of the equipment installed down on the rooftop of Salt Lake City. So this is some of the products from Skylark Wireless. I have no stake in the company, so it's no conflict of interest at all. The lesson we learned from Clay, he graduated in 2017. I thought about that, right? Over about 8 years, he basically did the same thing. No innovation in algorithm, no innovation in hardware. It's basically we take a newer and cheaper generation of FPGAs from Linux and we burn the same algorithm into it, right? So that gave him to think, why does it have to take 7 years? It's because FPGA, we're in the FPGA. Why should we use FPGA, right? So that got me to think even more. Like that time before the RINS project, people asked me, hey, massive MIMO is 5G, right? Millimeter wave is 5G. What is after 5G, right? My answer later on evolved into, after 5G, there should be no G, right? Think about Facebook or Google. Do we think of a Google 1G, 2G, 3G, 4G? No. Facebook 1G, 2G, no. It's because it's all implemented software in the back end. We have the same front end. The software keep on evolving. You don't need G at all, right? So that's kind of my dream, right? Hopefully after 5G, we don't, not we call NextG, right? Hopefully things will be able to evolve like software evolution, but it can be seamlessly continue to evolve. So that gets us to think about, can we move this painful lesson from Clay's PhD experience with FPGA and my epiphany about what's contrast with the wireless industry, mobile network industry, and the internet industry. Can we think, hey, maybe we should try to softwarize, virtualize as much as the wireless network stack possible. So that's basically then become the motivation of the RINS project. And if you look at the existing network, what you have is on the rooftop somewhere, you have dedicated hardware, special hardware on the rooftop. Here is actually, if you go to San Francisco downtown, on one of the rooftop, you will see LTE and 3G base stations, boxes from multiple carriers, right? And what we dream about is we could disaggregate the radio access network, move the computation away from the rooftop and consolidate them into a multi-tenant edge data center. For example, one for entire San Francisco metropolitan area. And that with fiber collection between the RU and the edge data center, we should be able to do all the processing here. And even better, you could share this edge system with other latency sensitive applications like AR, VR, self-driving cars, etc., etc. So our goal for this RINS project is to virtualize the massive MIMO, which is considered what most computational intensive wireless radio so far. So we have basically done that. We show with 4 Intel Gen Go processor, and we'll be able to run up to 64x16 MIMO, just one processor. Right? Of course, with 4 cores, 4 sockets with 4 CPUs, right? And then one processor. And we have the software, it's open source, called Agora, is structured as a worker manager, a model that implement the entire physical layer. Unfortunately, not in the 3GPP compliant manner, but we try as much as possible to follow the frame structure of 3GPP. It does everything from FFT to LDPC code. So this is, we can, in 3GPP, they have this multiple splits between RU and DU, right? We are basically going by the most challenging one, right? Split 8, we try to do everything in the DU, right? Have nothing, only have IQ sample coming away from RU to the DU. So we're able to, this is the result for 1 millisecond frame for uplink, which is more compute intensive. We basically find with only 26 cores, you can basically even meet the 5G EMBB profile and go up to 64 by 16 MIMO.
What's the bandwidth?
What's that?
What's the bandwidth? Do you
This is
remember?
20 megahertz. 20 megahertz. This is a CBRS spec, okay, within the Skylab equipment. We did experiments with real RU and EU. Again, use the Skylab wireless equipment. This is RU. They have FPGA inside, but we just don't play the FPGA. Get IQ sample out, send to the server, runs the signal processing software, and then we have mobile clients talking over here. And using experience, we basically show we can achieve block rate that meets 5G target with 6-4 RU and 10 ADUs. We want to be so now our trajectory change from what is a computing problem to what is a software problem. Of course, I think the hardware is radio frequency is a hard problem, but people are saying you always convert the problem into nail that you hammer, right? So software guys basically convert problem to solve problem. So the for this range project, what we really want to do is with software achieve flexibility, right? You can evolve, you can update all the time. We really want to achieve scalability and elasticity, which also include efficiency. Because once you switch to software, compared to ASICs, the energy efficiency is 500 times worse automatically, right? How can we leverage elasticity, resource density to compensate some of the efficiency loss? That's one. So these are some results from our prototype, right? So some interesting thing is, number one, as you adding more cores, so the x-axis you can consider this adding more cores, more workers, and the physical latency is starting to drop and then eventually go up. So that means this is work inflation in parallel computing, basically. So that means for any of your MIMO configuration, you have to figure out what is the optimal number of cores worker to use. It's not always the more workers, more cores, the better. Well, sometimes when you use more cores, actually could end up, of course, higher latency, lower efficiency, because inter-core communication. So we take we monitor, we kind of zoom in the performance of our prototype. You can see the different stage of the tasks, right? Like the blue one, the FFT, this is about 13 symbols. And the green one is eligibility code. The yellow one here is zero forcing precoder calculation, which is compute intensive. So you can see this time, this is thread ID, which is cores, number of cores, right? In this case, we use six cores, right? So you can see there's some of the things interesting is a lot of white gaps in between, right? That means these cores are idle, not doing anything. Right, so that turn into waste of energy and waste of computational power. Imagine you run this on multi-tenant data center. These are the opportunity you could have used for other computation. So one of the goal for this RINS project is, number one, how to design the implementation so that this can be more competitive, less white space here. Number two, for some white space, how can we quickly switch to other workloads, okay, to improve elasticity. So this is kind of the RINS project we've been working on in collaboration with my colleague, Professor Arnold Novo from Yale, and he's an expert in cloud computing. Basically, two of us together try to achieve, improve the elasticity, elasticity efficiency, and also scalability. So the It's briefly goals, and then let's talk about give updates. Scale up. How can we? I mentioned we have already achieved the 16 by 6 4 by 8 MIMO, right, in real time with software. It's actually we want to go to 256 by 64, even larger scale for the next generation standards. And that requires us to use the cores even more efficiently. Even within one server, how can you scale up and reduce inter-core communication, and by allocating the task efficiently to do that. So for this, we have been talking to our Intel collaborators, getting input from them about their development FlexRAN, and using tricks Intel have the FEC eASIC cards, which basically accelerates the most computational intensive part, which is LDBC code, put in the eASIC that will be take the computation off, I would say 60% of the cores, so allow the system to scale up even more. So we have got a couple of cards from Intel, and so so second goal is to scale out, right? Use resources beyond one server, right? Typically, this high-end server with 9 cores is more expensive than, let's say, 4 commodity server, each with 25 cores, right? So we'd like to think about how to use a cluster of commodity servers, and also think about a rank of servers. How can we even build larger scale MIMO? In particular, we're interested in a scale like a co-MP style, like multiple RUs, like a time and a frequency synchronized that could send their IQ sample to a shared data center, and there you could join MIMO distributed RUs. So that we have, for this cluster, we have made progress using a shared memory, software shared memory implementation that allow a broad run of a cluster of 4 commodity servers. We're looking to the synchronization of the RUs used these days. You will, we're trying to find an atomic clock these days are very cheap. You can buy like $3,000, you can buy one tiny one. You can put into its RUs to get them to synchronize in time. And through that process also where GPS become possible, because atomic clock becomes so small you can put in satellites. Now they're even smaller, even cheaper, you can put in base stations and to achieve co-MP style communication. Okay, yes, last to go. Research is, so we were looking to how to borrow ideas from the cloud computing, such as serverless computing, that we could dynamically acquire cores, release cores, right? We imagine our physical here run in a multi-tenant environment that you can acquire cores as you need, right? When the loudest traffic goes up, you get more cores from the infrastructure vendor. When the traffic goes down, you release them back, right? So this is how can you do this efficiently, quickly, and how could you use things like machine learning, reinforcement learning to learn about once you know I want to do 256 by 8 MIMO, right? How many cores I need and how many actors I need to provision the resource to the system in time, that's what we're working on right now. So last slide, I think that we have been working closely. I have monthly meetings with Intel folks about the possibility of integrate some of the results into their FlexRAN project. That has been ongoing conversation. Number 2, 3GPP compliance. We give up, right? We realize it's like beyond our resource, our capability to make our implementation 3GPP compliance. It's a tremendous amount of effort, but we are happy to collaborate with industry and to see how our research results, how some implementation maybe get integrated into their 3GPP compliant implementation. And lastly, I think as in university, I really think the project allow us to have a lot of collaboration between EE and computer science these days, and how allow us to teach wireless as an interesting workload in computer science. These days, everybody interested in AI, but we'll try to get people to think that wireless too. But actually, if you look at the physics layer, AI and wireless physics layer is it's basically matrix, right? Arithmetics, right? It's all connected.
And similarly, I want to introduce computer system curriculum into the wireless curriculum as well. Okay, thank you.
The next speaker is Krishna Narayanan from Texas A&M. Next slides.
Can you do a should start with the time.
This is the shared one.
It's supposed to download all of this on the locally. Yeah.
Oh, shoot.
You just upload it. Yeah, so probably just hook it up like Ali did.
Okay, perfect. What do you do with this?
It
Choose the most liked presentation on the or project.
Secret letter.
Yes. Then hold it. Collect. You get through. So just write the PI name on there, your favorite presentation or project.
When do we have to submit it?
At the end of the session. We'll collect it.
Oh, great. Was that only two? That was only two.
Yeah.
Thank you. My name is Krishna Narayanan. The original title of the project is a little bit different from the title of the presentation that I'm going to give today. The main goal of the project was to build a resilient uplink for wireless communications, particularly that would embrace this cell-free paradigm. And
oh, I need to find the receiver for the clicker.
So we've had results along a few different topics within the big team. So in fact, this week, my colleague Jean-Francois is presenting our results on designing new kind of multiple access based on what we call a sparse regression LDPC codes at ISIT. So this week turns out to be one of the big information theory conferences. So he's presenting it at that conference. We also have a couple of other results along this. But what I'm going to talk about today is about using transformers for solving some canonical problems in wireless communications. Of course, once we started the project, we made progress along these lines, but a lot of people got excited by ChatGPT and transformers in late 2022. And so we started doing something along these lines, which was not originally in the plan, but I'm kind of excited by this, and so I'm going to talk about this. Before I do that,
Ali inspired me to just say a little bit about student training about the project. So we had 3 grad students who worked on this. 2 of them interned at Qualcomm last summer, and they're going to join Qualcomm as full-time employees in September. One of the students is currently interning at Ericsson, also one of the Rings partners, I guess. We had an undergraduate student, Holly, who was in my class when I taught a signals and systems course, and she did her undergraduate thesis with me. And like Ali mentioned, she got inspired to continue to grad school. She's now a grad student at Texas A&M University as well. All right, so 15 minutes is not a lot of time. I cannot give you a lot of details about what I'm doing, but I'm going to try to hit a few important things, and I'm always available to talk offline. So, ChatGPT obviously has created a lot of interest in transformers. We don't really fully understand how large language models work, but it's pretty clear that they do a few things very well. At least there is a lot of empirical evidence that they do a few things very well. So they are very good at predicting the next token in a time series. They're very good at predicting time series. And they're also very good at what is called as in-context learning. To give you a very quick example of this, if you go to ChatGPT and if you simply type Q relativity, A Einstein, Q gravity, A Newton, Q information theory, A watts, telling it nothing more, it correctly gives you the answer, says it Shannon, right? So the idea is that it's able to infer some relationship between these question and answers without being explicitly prompted to do this. So what we started thinking about was to say, okay, what do these things mean for wireless communications? Can we use this to solve canonical problems in wireless communications? And that's basically what I'm going to talk about. So we have a few results along this. At the last meeting, Rings meeting in October, I presented the things that are in blue on this slide. So we showed that you can use transformers to do excellent compression. In particular, I'm kind of blown away by how good they are at losslessly compressing English text. I'm not going to talk about it today, but that's one of the results we have from this project. And essentially what this entails is using a very large language model, both at the encoder and the decoder, in order to be able to compress text. So what we did in the last year, everything that I've shown in the red is stuff that we have done since the last meeting that we had in October. We were motivated by a scenario where your mobile may be doing the compression, but the base station may be doing the decompression, which means your mobile is probably running a small large language model, and the base station has the ability to run a very large model. So in this case, we thought the small model might still leave some redundancy that you can exploit by running a bigger model at the base station, in the typical joint source channel coding paradigm. But we realized we were a little too naive about this, and it turned out there are several issues that we have realized. So we have not been able to solve this issue, but this is what we are thinking about. We are thinking about joint source channel coding problems where you run simple models like on a handset. Qualcomm probably has an efficient LLM that they run on the handset, and you have a bigger decompression algorithm at the base station. But in the next few minutes, and this is what I'm going to talk about, I want to show that classic estimation problems can be cast as what we call as in-context estimation problems. And I want to make a case that transformers are somehow very good at solving the problem that we want to solve. We don't fully understand why, but we have spent quite a bit of time in the last week to get some theoretical results. We're getting some understanding of why these transformers are doing these things. I'm not going to say that I fully understand what is going on, but the typical kinds of flavor, I'll tell you the flavor of results that we can get. It's far away from solving everything, but that's the first theoretical step, I think. So the problem we were interested in is this. It's the classic problem on the uplink. I have a user who's at the edge of a cell. User has a single antenna. Base station has D antennas. D antennas at the base station. User transmits a symbol. It passes through a channel H. I observe Y, and I want to make a decision on what X was transmitted, right? The problem is nobody tells you what the channel is, so you have to do something to estimate the channel. So I'm going to assume that you transmit K pilots, so you get to observe K of these Ys, Y1 through Yk, and you know X1 through Xk. and then you observe y k plus 1, and then you want to figure out what x k plus 1 is. So any estimation of the channel that you do is really implicit in the process, because ultimately you care about making a decision on the symbol, right? Now, the key thing that motivated this work was to realize that, if your user is at the edge of the cell, then the SNR for the user is very low, that you need to have a good prior on the distribution of the channel. If you get any good prior on the distribution of the channel, any Bayesian inference would take good use of this and would do a good job of estimating the channel. Otherwise, the performance suffers quite a bit, right? So this was the main motivation. And why did we think of transformers? So the connection I made was this. So, if your transformer is really good at answering these question-answer things, so why don't we think of it this way? I'm going to think of my first received value y as a question, and I'm going to tell the transformer that the transmitted pilot was x1. So I'm going to tell the transformer these k question answer pairs, and I'm just going to give the k plus 1 y and ask the transformer to guess x, right? So this was the hope that it would do well. And this is so what we did. And particularly I was also interested in this case that, there is this notion that the transformer is somehow learning the hidden context between x and y. And to me, it seems like when you model a wireless channel, I'm going to make a case that a hierarchical model is a more accurate model than simply modeling it as using Gaussian or with any kind of covariance. And the reason for that is I'm going to give you two scenarios, right? So think about a scenario where you don't know the type of scattering. So let's say you are outdoor, you have a line of sight to your base station, you get a single ray between the transmitter and the receiver, you are going to get a certain kind of correlation across what you receive at the antennas. At the other extreme, maybe there is rich scattering. There is no line of sight. You get a very bunch of diffuse components. So you're going to get a completely different kind of covariance at the received signal. You're going to get IID fading essentially. Of course, truth may be somewhere in the middle. Maybe there are nonlinearities. Maybe there are all kinds of things, right? In reality, we don't really know what exactly the distribution is from which you draw the channel. So it seems to me that what you should say is there is a context. In this case, the context is given by the type of scattering. And once you have a context, then you draw a realization of the channel. Did you?
No, it's just stretching, sorry.
Okay, and here is another classic example. I may have mobility, but I don't exactly know the speed, right? Maybe I'm moving slowly or I'm moving very fast. Nobody tells you what the exact speed is. And depending on the speed, you have a certain covariance. So the context in this case would be the speed, right? So then, I think I'm going to skip this slide. So what we did then was to do the following. We trained a transformer. So we took something which is like a GPT-2 transformer, not very large, but not really small either. And then what we did was we trained the transformer in the following way. We first pick a context. So, maybe we pick a high speed, 30 meters per second or something. We generate a realization of the channel with that particular speed. And then we tell the transformer, we give this Q&A to the transformer and ask the transformer to get X. And then in my training set, the next training data is created by drawing a different context or randomly drawing a context and then drawing a realization. And the key thing is that over one set of Q&A, the context remains the same. Right, so this is the most practical scenario. So maybe you are traveling very fast, and then you transmit a bunch of pilots. You're supposed to estimate X, right? And then for now, we are asking the transformer to minimize the mean squared error in predicting XK. But I think this is not a big problem. We can change it to cross entropy or whatever we want. I don't see that as a real big problem. Okay. And then we train the transformer, and what I want to show you are some set of results. Oh, thank you. So here is a set of results where what happens is this. So I take one of two possible scenarios during training. I say that either you have a one-ray model or you have rich scattering. So the transformer is trained on both these contexts. But during testing, I pick one of the two. I pick a realization from a one-ray model and then ask the transformer to do the prediction. And this set of, these results correspond to the true environment during testing being the one-way model. So what I plot here is the mean squared error as a function of context length, which is the same as number of pilots, and how the performance changes as the pilot increases. And what I want to show is this. So this is the performance of something that's agnostic of the context. So basically, it would use the average covariance of both these two things to do the prediction, and clearly that's not very good. The lower bound, so this is the performance of an estimator to whom the context is given. So a genie gives the context to the estimator, and then the estimator does its job of estimating the channel and doing the estimation. And you can see that this is the performance of the transformer. The transformer does more or less close to that of the lower bound. It's as though it's able to infer the context from just the pilots and apply the correct estimator. But there is something more intriguing. Now we go to this scenario where we have mobility as the unknown. And something very interesting happened here. I have exact same set of results. Pilot length this way, mean squared error. And this is for a very high speed scenario. Okay, something very high so that we want to test something. So this is again the agnostic estimator. An estimator which averages the covariances over all speeds. Very bad idea. The green is the lower bound, but something really interesting happens. So this dark blue is the performance of the transformer. The light blue is the performance of the optimal Bayesian estimator. In this case, we were able to compute the optimal Bayesian estimator. What I mean by that is, so in this case, there were 3 speeds in the training set, right? So an optimal Bayesian estimator, what it would do is it would first form the posterior probability that the actual channel came from one of these 3 speeds, and then it would average the performance over these 3 speeds. And the transformer seems to stay right on top of the Bayesian estimate. So it's not, and the same thing happens at all speeds. So we started thinking, okay, maybe the transformer is actually making the exact Bayesian estimate, and the question is, can you really verify this thing? Right now, I cannot prove it, but it seems intriguing that it's actually doing something like this. The next thing we did was to understand, we threw a GPT-2 at it, it's fairly complex. So we are trying to figure out, what is the least complexity that you can get away with. And it turns out that you do seem to need reasonably large complexity. There are 2 things from which the complexity comes. One is the embedding size. In the transformer, there is an internal embedding size. And it seems like you do need fairly large embedding sizes. You also need to have fairly large number of layers. The last thing I want to show is, and after I presented our results last time, a nagging question we had in our mind was, is there anything special about transformers? Could I have simply thrown a fully connected neural network at it? Could I have just thrown an LSTM or any one of your other machine learning models? And is there anything special about transformers? So at least empirically, we see that these other machine learning models are not matching the performance of the transformer. So the transformer seems to be doing something that at least these LSTMs and the fully connected networks are not doing for this particular problem. So the last thing, I have only 1 minute, so I won't be able to show the proof, but I will tell you the flavor of these theoretical results we can get. So what we can show is this. We can show that if you consider just a 1-layer transformer, clearly not a strong enough machine learning model, but just a 1-layer transformer, but if you increase the number of pilots, then the 1-layer transformer is expressive enough. There are a set of weights that you can choose for the transformer to be able to form the correct Bayesian estimate in the limit as the number of pilots becomes large. So at least this tells you the transformer, we know for a fact that it has enough expressivity to be able to implement the correct estimate in the simple case. But of course, in practice, we don't care about infinitely long pilots. We want to reduce the number of pilots as much as we can. But there, I think the theory is not strong enough. We're trying to understand the smaller 2 or 3-layer transformers right now, but we don't have anything on that front. So I think I'm going to stop here. Maybe last one I will flash with a bunch of questions that we are thinking about. I said that they run. Should I stop? Yeah, it's okay. I'll stop with a bunch of questions I'm thinking about. These slides will be available to you if you want. You can take a look. Thank you.
Very cool.
Yeah, video. It should come in. Oh, let me share my screen. Oh, it's not connected. I think it's on his laptop. The
Oh, the dongle.
the dongle. Oh.
Oh.
Thank you.
Okay. Morning, everyone. My name is Kemal Kaya. I'm from the International University. So Reza was supposed to come today to present, but he's late, so I'm replacing him. I'm one of the co-PIs. And this project is a little off-topic compared to the other presentations on wireless. So we're going to discuss how to bring post-quantum cryptography to NextG systems. I try to keep it in layman terms so that you can follow. So when we started working on this project, our goal was to bring post-quantum algorithms to different components of 5G, starting from the UE side to the core network. And so this included investigation of algorithms for the UE side for we considered IoT devices that are connected through 5G. And then how can we design software, hardware solutions for them? And then when we like to transition these solutions to the protocols currently used for 5G control plane, how can we test them and what are the performance trade-offs when you switch to those algorithms? So basically, shown here, so it's considering all the layers starting from the user device, and we consider IoT devices that don't have enough resources. So how can we customize the solutions? Because these are cryptographic algorithms. And then when you consider the protocols starting from the UE RAN and then 5G core, there are a lot of control protocols that use security algorithms, and they need post-quantum algorithms when we envision a future where we have quantum computers, and those quantum computers will be able to crack all the existing solutions right now. Most of them actually will be obsolete. So the solutions that we use today for securing internet will be obsolete, and we need to replace them with post-quantum algorithms. And this is a general effort actually from NIST, that they started to design post-quantum cryptography solutions. And you see here, there were competitions in different rounds, and eventually they selected these algorithms for digital signatures and for exchanging a symmetric key between two parties. And these are being standardized by NIST. And this was a huge effort, and this is independent of this project, but we are trying to bring these solutions, these exist, and test them on 5G environments with their pros and cons. And it's not just NIST, by the way, there's also NSA has its own framework for commercialization of these algorithms, and they have different standards. But the problem is actually when you look at the post-quantum cryptography algorithm designs, it started 2018. And there's been a lot of algorithms designed, and unfortunately, most of them were cracked. So these are just showing the names of different algorithms, and they have been cracked at some point, and therefore it's a risk. So we have these solutions today
And we don't know what will happen tomorrow if there will be a hack or not. But this effort is ongoing, and we wanted to bring this to NextG systems, whether it will be standalone post-quantum cryptography or hybrid solutions or composite solutions. So hybrid means you can actually use both solutions. Like right now we're using RSA and ECC, but if you consider a hybrid solution, then you will take one of the post-quantum cryptography generation 1 or 2 and merge them. Actually, you're doing two signatures for certificates, or you can do a composite and you can use a new algorithm that will bring the benefits of both. So the hybrid is one of the things that people are considering for a future, because if one of them is compromised, if there's something, the quantum algorithm is compromised, and you can use a classical, or if classical is compromised, you can use a quantum. So this is ongoing. But what we did in the project, there are 3 universities. So Florida Atlantic University was focusing on the UE side, as I said, the IoT device. How can we develop primitives, the hardware or software for post-quantum cryptography deployment? And then Marquette University was focusing on how to manage the certificates. These are post-quantum certificates on the core network side. And at FIU, at Florida International University, we were trying to integrate all these on 5G testbeds and test different protocols that bring security to 5G operations. So this is one of the one of the results from the FAU. What they did is that I was talking about this hybrid implementation of post-quantum and classical cryptography to be integrated with TLS. So TLS is the protocol that we use for securing internet communications, but that is also the standard, the upcoming standard in 5G. Right now, there's going to be a transition from the AKA protocol that 5G is using for user authentication to this TLS version. So TLS 1.3 will be from 3GPP's recommendations. This will be the next on 5G, and it doesn't support post-quantum right now. So what they did is they merged these two solutions with, so Dilithium is one of the post-quantum algorithms, and ED448 is the classical ECC, and they wanted to combine and come up with a new protocol, actually an extended version of TLS, and this was tested on ARM Cortex microcontrollers, and there was obviously there's an overhead of 2.67 compared to the classical only. So this we plan to take this. So this was tested standalone. We plan to take this to our 5G environment and test on the test bed. What we did at FIU is we looked at we actually last year we developed a virtualized 5G test bed that you can test all the protocols from the UE side to the core network. And on this test bed, we wanted to see how can we integrate post-quantum into the control plane of 5G. So in control plane, there are a lot of protocols that require security. For instance, in the core network, there is this network function registration protocol. At the UE side, we have the UE registration and authentication. And these are all dependent on certificates. Those certificates should be replaced with post-quantum certificates. And what we did at FIU was to create solutions that will bring these post-quantum certificates and give us the ability to test the performance compared to the regular current implementation. So we actually utilized TLS tunnels so that this can be integrated to, there are open source solutions, but it's not possible to test post-quantum there. You need to write code from scratch in order to enable post-quantum certificates. So what we did is we created tunnels starting from the UE side. So UE and the G-Node B, they are sitting at different machines. Actually, we tested this on the cloud, Google Cloud as well. So we created these TLS tunnels between each of them, and this gave us the ability to force post-quantum certificates to these protocols. For instance, this one here from NRF to SCP, there is a protocol. They rely on security, encryption, and integrity. So TLS provides that, and we integrated it. We use post-quantum certificates. Same for the UE side. And when we tested it, this showed us that we can actually utilize one of the existing post-quantum certificates called Falcon. And it actually performs as good as RSA. That means that we will not have any additional overhead when we transition to the post-quantum. And we made this available on our website, and we are currently looking at doing more experimentation with the different configurations. Okay, so some of the challenges that we face here is on the UE side when you like to do implementations. Really secure implementations is a challenge because you may have so-called side channel attacks. So even if you have a secure implementation on a device, you can have side channel attacks. So we are dealing with these still. There's ongoing work. And then if you consider IoT devices and use something like narrowband IoT, this creates challenges in terms of some of the signatures. Post-quantum signatures, they have a larger packet size, and this impacts the performance. And I guess the most challenging part is the current. You're using open source implementations, but they are really difficult to integrate and work with, and they have different APIs, and interoperability is an issue. If you want to make changes, it's difficult and require a lot of resources. So this is actually related to this first challenge here. At FAU, we did a test on understanding this side channel attack protection. So if you want to provide that protection, you need to implement the algorithm. For instance, this Kyber is one of the post-quantum algorithms in a different way. So if you do that, so if you don't have the protection, the clock cycles are similar with respect to the classical cryptographic solutions. But once you start implementing first order, second order, third order, see that Kyber overhead is really going up significantly. That means that even if you want to use Kyber, if you want to enable this side channel protection, then it will probably be a big challenge in practice to deploy. And so as a future work, we're looking at hardware, software co-design. So it's not possible just to deal with the secure implementations in software. It may require hardware integration. We want to do more testing and evaluation with the core control protocols. We did TLS, and we want to test hybrid TLS developed by FAU. We want to consider other PQC protocols to be integrated into TLS, and we want to look at the certificate revocation overhead on the core network side when we use post-quantum certificates. So this is just a high-level summary. If you're interested in more details, I'll be happy to talk to you.
Thank you. Right, so that brings us to the end of the first session. We'll take a very short break, I guess, at this point. And then I think Raj is going to take over for the next one.
Yeah, so the next session starts at 11 o'clock. I think we have only 1 or 2 minutes. What's the plan?
So don't forget to vote if you have your cards. If there's anybody want to vote for. Let's give folks like, we can do like a 10-minute break, and then if we sort of make sure we go quickly through the
10 after 11, maybe.
yeah. So be back here at 10 after 11. Just see all the
So the vote is for one day, for each.
I don't know, is the vote for the whole day or is that
Each session?